Hello, welcome to Meeps Math Matters. It's been many years since I've done this. I'm rebooting this because I want to explain a variety of phenomena that we've been seeing lately, and I really need to build up the language so that others who are maybe not, are quantitatively minded but may not be as familiar with probability. So this is not going to take the place of any course. Don't worry about having to uh, calculate combinations or permutations. I'm not even going to touch upon that. If you're looking for help with your homework, no, I don't do that, and go somewhere else. There are plenty of videos for that. Khan Academy is very good. So let's get started. So just to touch on it for a moment, on the history of probability, it really got started in a rigorous way when a bunch of mathematicians, or just intelligentsia in general, were sharing letters back and forth, challenging each other to try to figure out how one should bet in certain dice game. Obviously, gambling was very popular at various points in time. It's actually always been popular. But some of the bets were starting to get very complicated. And some people notice that maybe there's a pattern to them, even if the dice aren't loaded. And we can talk about loaded dice another time. So the question is, how should you bet? Or is something a good or a bad bet? We'll be working up to that. The next one I'll do after this will be on expected value, and that will relate to whether something is a good or a bad bet. But let's bring probability back perhaps to something a little more everyday. What's the probability that it's going to rain today or it doesn't rain today? And we're going to assume the way we define it, I'm not trying to be tricksy here, either it rains or that doesn't happen. Something happens or it doesn't happen. This is not a Schrödinger cat kind of thing. Looking outside, it's pretty sunny, but it's springtime, weather is changeable. So let's say the probability of rain is 5% and probability it doesn't rain is 95% then. And that will bring us to our first law of probability. And that is all the probabilities, or the probability that something happens plus the probability that something doesn't happen, has got to add up to 1. That's going to be our first, actually, it's really the second rule. And so we'll get into what the rules of probability are. So the first rule of probability is probability, and this is the notation I'm going to use. I'm trying to stay away from really complicated notation. I don't want you to have to learn any notation whatsoever, okay? I'm just trying to keep it pretty straightforward. So the probability of event A, and that's how we say event, but probability that something, and we'll just use A as a stand-in as that something, could be rain, could be win a bet, could be all sorts of things. Probability of any given thing occurring has to be between and inclusive of 0 and 1. If the probability of something is 0, that means it cannot happen at all. And if probability is 1, that means it's sure to happen. Now, that's very unlikely in the real world. There are a few things that are 0 and 1, but ahead of time. And then, of course, after the fact, we know what happened, don't we? There are no negative probabilities. There's no probabilities greater than 1. So that really is the simplest, just starting out, that's probability, first part. Second rule. The second rule is the probability of not A. So the probability of A not happening equals 1 minus the probability of A. So if you have A and not A, you add them together, they have to add up to 1. They are exhaustive. And actually, these will extend to, if you can enumerate, or however you want to say, break it up, break your probability space, to get technical for a moment, into all possible exclusive events, and I'll talk about that in a moment, all possible exclusive events. If you sum up the probabilities of all of them, it has to add up to 1. And that's going to be what follows from this. I'm not proving this, I'm just letting you know. If you have all possible events that don't overlap, and the word we use for it in mathematics is exclusive, those have to add up to 1. So again, some language for you to be familiar with. If there are exclusive events, A and B, okay? So rain and doesn't rain. Those are two exclusive events. That means they can't both happen. So probability of A and B, meaning both of them happen, probability of that equals 0. So the probability of it rains and it doesn't rain, where it's rigorously defined. We're not doing any of this chop logic kind of crap. Okay, it will be very cut and dried in the applications I'm going to be using, such as the age at which somebody died. They didn't die at age 70 and age 80, a specific individual, unless they were a zombie, and we are not positing that, okay? Again, we're not doing fictional stuff. It's very cute for us to think of these things, but I'm trying to be serious because I will want to build up this language and build up this knowledge of concepts to life expectancy, to expected value with regards to finance and investments. And we need to have a language that we can use so that this makes sense. So let's look at what we call probability distributions, or I should say, different, very specific and very simple versions. So first we're going to start out with discrete. And discrete distributions just means, and I'm sorry, I want to be specific here, all the distributions I'm going to have from now on are going to be on real numbers, okay? I mentioned before I could say probability of rain doesn't rain. When you start out in probability theory as a math major, probability spaces can be over any kind of thing. Set of events is what we call it, and that gets mapped to random variables and yada yada. We're not going to worry about that. All I'm just going to say is all I care about now is distributions over numbers, real numbers. Later on, it may be tuples, or just basically a sequence of numbers of a finite length, like 2 real numbers. So you throw 2 dice and you look at the numbers on, say, a red die and a green die, and you get those 2 numbers. Those will be the numbers that we're going to be looking at. We're not going to get too complicated, though. We're just going to start out. Here's a discrete distribution. It's uniform on 1, 2, 3, 4, 5, 6. So this would be, say, a fair die. We roll it, and we get a number back, 1 through 6. And the probability of any given number on one roll is 1/6. Okay, that adds up to 1. All of these are between 0 and 1, so we're fine. So let's say we still have a distribution on 1, 2, 3, 4, 5, and 6. But the probabilities are now different. We'll say that the probability of getting a 1 is 0.5 or 50%. For 2, it's 0.1 or 10%, 3, 4, 5, and 6, each 10%. If you add these all up, you'll notice these add up to 1 as well. This is just fine as a discrete probability distribution. And we often call this a probability mass function. A probability mass function for these discrete distributions when we're doing all sorts of calculations and you see formulas and stuff like that. We're not going to really bother about that too much. So now let's consider continuous distributions. And there are mixtures between discrete and continuous. Again, not getting into that right now. But you may have heard of something called a uniform distribution. So here I'm talking about a uniform distribution between 0 and 1. So these are real numbers, any continuing fraction, etc., that you can think of between 0 and 1. And you may be wondering, how do you figure out probability? At least with discrete, you understand, okay, if I want the probability that I rolled an even number, on the dice. I can do the probability of rolling 2 plus probability of rolling 4 plus probability of rolling 6. Those are exclusive events. You can't roll a 2 and a 4 at the same time in the same roll. So that's one. But how do you do that with a continuous distribution? And again, we could get into the philosophy. The probability of any specific number coming back from a continuous distribution is 0 if it's a purely continuous distribution. So that makes life a little difficult to deal with. So what we do, and I'm going to demonstrate this with the uniform distribution because it's a lot easier, is there's something called the probability density function. And with the probability density function, what it is a function. It's non-negative, and that's all that matters. And then the area under the curve, and so when I say area under the curve, I mean from the function, so from the height of the function to the horizontal axis. So we usually call that the x-axis. If we were doing calculus, this would be the integral of the PDF from negative infinity to positive infinity. That integral has to be 1. And that's the only rules that we have here. Now, for practical purposes, how do we deal with this? Basically, you have to give me a range over which you want the probability. If I want probability from 0 to 1, this is a uniform over 0, 1, then the area of this whole thing is 1. Yeah, I know this doesn't look like a square, so excuse me. The vertical axis and the horizontal axis are on different scales. That happens all the time. So I have a rectangle, height 1, width 1. There you go, probability 1. So let's make it easier. So what's the probability that it's between 0.2 and 0.5, and it doesn't matter if you include or don't include the endpoints here. So basically, again, it's that area. So from 0.2 to 0.5 on the x-axis, so horizontally, that width is 0.3. And again, the height is still 1. So the whole area there is 1 times 0.3. So that's 0.3 or 30%. So the probability is 30%, which is what we would expect. So that's all you need to know about probability. No, I'm just kidding. Obviously, there's a lot involved in probability, and a lot of the undergraduate introductory probability classes will focus on some very well-known distributions. One in particular is the normal distribution or the Gaussian distribution, and I will be talking about that more later. So this very, very roughly is a probability density function for a Gaussian distribution, which is, of course, named after the famous mathematician Gauss. So what do you need to know at this moment in time about the Gaussian distribution or the normal distribution? And later we'll find out why is it called the normal distribution. We're going to start out, and I'm going to set the mean, so the average, and that will be in a future, actually the very next lecture in the series is going to be on what is the mean or the expected value of a probability distribution, whether it's discrete or continuous or any combo thereof. Okay, so but we're going to have this centered at 0 because this makes life easier. So this function, this probability density function, is supposed to be symmetric, and my drawing is kind of lopsided. This is not intended to be lopsided. It is supposed to be symmetric, okay? And that means, of course, the probability, the function value at, say, sigma and negative sigma should be the same height, okay? I just didn't draw it that way because I suck. Okay. It has certain properties, and it does go out. It's non-zero for all real numbers as far negative as you want to go, and that's what negative infinity means. It means as far negative as you want to go and as far positive as you want to go. And then the area under the curve, so if you integrate from negative infinity to positive infinity, well, you end up with 1, okay? That's what makes it a PDF, a probability density function. Okay, But this underlies a lot of statistics and a lot of reasoning we have about all sorts of things in real life, and the basis of insurance to a certain extent, which is the central limit theorem, which I am not going to explain to you what that is today. We do have to work up to that. It requires talking about what expected value is and what variance and standard deviation are. Okay, so I use this, it's supposed to be this little Greek letter, lowercase sigma from the Greek alphabet, and it just means sum. But it has certain properties, and the Gaussian is a family of distributions. You can have any mean. I'm just showing it around zero because it's just easier to define symmetry around zero than around some other mean, which we usually use mu, which is the M of the Greek alphabet. That about 1.96 of this parameter we call sigma, the Gaussian is completely characterized by its mean and its standard deviation. You don't need to know what that is right now. If we go from negative 1.96 sigma, and this is approximate, to 1.96 sigma, and we get that area under the curve, that's 95% of the probability. Isn't that interesting? That 95% comes up every time you see something about they polled 1,000 some people, and we say that about 48% are for this or for that, with a plus or minus 3% margin of error or confidence interval. This confidence interval comes from Gaussian distribution, and we'll see why they do that and why they think it's true. So let me pull back on this canvas I've been writing on for all of these lectures, or this lecture, I should say. And we can see some of the concepts we have here. This just lays down at a high level for our next steps. And remember to spread the math love. See y'all.